Hi there, my name is Valerian and I'm going to be talking to you about my final year project, the Standalone Physical Modelling Synthesizer. The aim of this project was to create a playable musical instrument that creates its sounds entirely through physical models. These are models that simulate the properties of real-world instruments, such as strings, bells and marimbas. Here is a year's worth of work in attempting to get those models to a point that they're playable in real time with adjustable parameters and with enough polyphony to perform expressive musical pieces. At the beginning of this project, I aimed to get a variety of models playable. These were a 2D plate model, a xylophone model, string, tube and woodwind models. All of these models, with the exception of the 2D plate model, are playable in real time. While developing the synth, I've added to previous models with optimizations to increase performance and allow the models to run in real time. These include adaptive downsampling, a modified linear interpolation method, and the use of lookup tables to perform faster mathematical functions. Furthermore, I have designed and created an enclosure and supporting circuitry to be able to play the keyboard. It only requires a speaker and power. A screen has also been integrated to display the current patch and model settings. So why make a physical modelling synthesizer? When Yamaha's initial physical modelling synth, the VL1, was released back in 1994, the media and experts alike expected that this would be the end of sample-based synthesizers. Now, 24 years later, this didn't turn out to be the case, and only a few physical modelling synths have been created since, compared to other forms of synthesizers, such as FM or additive synthesizers. This project aims to build one of these physical modelling synths, while integrating new findings from papers and using modern hardware. I chose this project because I've always been interested in finding out how digital audio works, and in this case, learning how to make new instruments through physical modelling. First of all, I'm going to give you a technical overview of how the synthesizer works. The brains of the synth is the STM32F4 Discovery board, while only being clocked at 168 MHz. This development board is both cheap and has an FPU, or floating point unit. This allows the board to perform quick, single precision floating point calculations. It also has many GPIOs and an integrated DAC for audio out. Connected to the board is a MIDI optocoupler circuit. This allows the board to read MIDI messages from the connected keyboard by converting current signaling to voltage signaling. Here's the schematic for that. An example MIDI message could be a note on command, or a command signaling that a control parameter had changed. Four LEDs are connected to signify the current state of the ADSR envelope that modifies the volume of each note. Here we have the power supply circuit, which is a typical 7805 linear regulator circuit with reverse voltage protection. The circuit provides 5 volts to the STM32F4 and 4.3 volts to the keyboard circuits. The circuit allows the synth to be powered by either a plug pack or a USB connection. On the software side, the code runs on bare metal with no real-time operating system. Originally, code was written for MIOS, which is an operating system that provided libraries to easily connect MIDI devices, screens and DACs. However, the current version didn't have proper floating point support. The synth now runs on third-party drivers by GitHub user Deadzy, which I found more clear to understand than the manufacturer's libraries. Here is the overall block diagram of how the software works. The main loop of the synth is a first-in, first-out event processor. Events are mostly generated by interrupts. When an event occurs, the appropriate function is called to handle that event. For example, if a note is pressed, an interrupt triggers due to the MIDI input. A state machine then determines the contents of the MIDI message and creates an appropriate event. When the main loop reacts to this event, it allocates one of the voices to this new note and begins exciting the relevant physical model, depending on which model is selected. So before going into each of the models in more detail, let's first go into some of the theory. This synth uses digital waveguides in the form of delay lines to generate sound, but how is this possible? I'll skip over some of the history and start with Taylor in 1713. Based off Newton's equations, Taylor derives the string's fundamental frequency. However, he incorrectly states that the harmonics or overtones of the string were only transient. More work was done in 1727 by Bernoulli. However, he also neglects these overtones. In 1742, Bernoulli's son, whom I'm assuming was a guitar or lute player, states that he can observe multiple modes occurring when he plucks a string. He's basically discovered superposition. 4 years later, D'Alembert writes an equation for this discovery, which states that the vibration of a string can be expressed as a combination of a left travelling wave and a right travelling wave. We can now use this equation to model a string in software as delay lines. We can have one delay line represent the left travelling wave and one representing the right travelling wave, and obtain the output sound by sampling a section of both of the delay lines and adding them together. That brings us to our string model, which I'll now explain. These reflection points represent the terminations of the string. The all-pass filters allow us to alter stiffness. Our base model states that all frequencies on the string are delayed by the same amount. However, a stiff string has overtones that are stretched out. This would mean that we would need to alter our delay length based on the frequency. How can we do this? Well, we could use an all-pass filter. Here we can see that by varying the all-pass coefficient, we can stretch certain overtones by changing the sample delay for them. This is hard to see on a plot, but here are some examples. Notice the fundamental of the note and the harmonics sound further apart as stiffness increases. Now let's look at a different element of the string model, the input into the delay lines. This is what it sounds like. A musical instrument usually works like this. A string is excited in some way, for example a pluck. The string then vibrates, and the vibrations are picked up by the body, or resonator, and transmitted into the air. Simulating the excitation and resonator separately is slow. Instead, if we assume that the string is linear in time invariant, we can commute the resonator before the string, and combine it with the excitation. Assuming the excitation is an impulse, this means that the excitation is just the impulse response of the body of the instrument. I recorded this with a microphone, processed it in a digital audio workstation to clean it up and shape the transient, and used this as my input. Let's focus on why we need interpolation in this model. Due to the delay lines being represented as arrays, they have a discrete length. When we want to tune a delay line to a specific frequency, we lose the decimal points. This means that the delay lines are always out of tune. We can fix this problem by making the delay line a fraction longer with linear interpolation, a way of taking a weighted average to extend the length of this line. Unfortunately, due to this taking an average, it also acts as a low-pass filter. This means that different notes with different fractional lengths now have different volumes, due to the low-pass filter affecting them all in a different manner. We can fix this by increasing the volume of the notes that are low-passed more. I found the value of the coefficient by running the synth output through a volume meter and adjusting the level of makeup volume with a knob until all the note volumes were equal. Lastly, we have an ADSR envelope on the output. The ADSR envelope, standing for attack, decay, sustain, and release, allows us to shape the volume envelope of the sound. This gives the player more options to alter the sound. The next model is the tube model. Hang on, you say, isn't that the string model slide? You're right, the only difference is that the tube model is excited on the end of the delay line, and one of the reflections no longer inverts the wave. This represents one of the ends of the tube being open. If you derive the wave equation for air pressure in a tube, you get the same result as our string equation. As we can simulate tubes with waveguides also, we can model a flute. Instead of an impulse response as an input, we can use white noise, an ADSR, and a sinusoid to model the jet of air into the flute. To model the time the jet takes to travel through the air reed, a delay is used, and to model the non-linearity of the air, a cubic function has been added. A low-pass filter models a reflection on the end of the flute, which outputs into another delay line that represents air circulating back up the flute. Finally, as the model causes a DC offset, a DC blocker has been added to the output. My favourite model is the banded waveguide model. This is designed to recreate the sounds of very stiff structures, such as bars. These are marimbas or xylophones. As we discussed earlier, stiffness means that the overtones of the note are stretched out. However, as bars are very stiff compared to a string, we have to model the overtones as separate delay lines. Here we can see 2 extra delay lines specifically added for the partials. We add bandpass filters to these delay lines to further tune them. These bandpass filters also ensure that we only get the frequency of the partial resonating. We can tune these delay lines and filters based on this recording of a marimba I found on the internet. There are 3 peaks I chose to tune the delay lines. One at the fundamental, one at 2.7 times the fundamental, and one at 5.4 times the fundamental. I then use these frequencies to tune the delay lines and set the cutoffs of the filters. This gives us a synthesized marimba sound. Comparing it to the sound of a recorded marimba, it sounds very similar. Another addition I made was adaptive downsampling. This halved the sample rate whenever delay lines became too long to store in memory. Without this, it would not be possible to play the low notes on the keyboard. When really low notes are played, aliasing can be heard because of this. The aliasing is easy to filter out, especially with the output low pass filter mapped to the modulation wheel. Additionally, the synth has a KARPLUS strong model implemented, which is essentially a delay line loaded with white noise, fed into an averaging filter. A 2D waveguide model was also implemented, which is essentially the same delay line, but extended to 2 dimensions. Unfortunately, the 2D waveguide could only run at 8x8 on the device, which doesn't leave much room to make a tonal instrument. Before we wrap up, let me talk about how I went about constructing the synth. The wooden part of the case was made using salvaged wood, and some wood I bought from Mitre 10. I ended up using mostly hand tools to cut and join everything. First I did the design in AutoCAD and made a few revisions to the front plate after prototyping it with wood. I then got the final version laser cut at the CAD CAM Centre at Monash. For the screen, I created the icons in Photoshop myself and designed a basic UI. So I think I've explained how the synth works. Now I'll answer some of the questions. High-level language and a more powerful device. A lot of my time was debugging low-level C code when I felt like I should have been spending that time improving my modeling algorithms. The first time I got audio out of the device, it was just a beep, but it was amazing. Thanks for watching my video. I think that physical modeling is going to be the future of synthesis. However, to get to this point, more practical implementations of models need to be built. As computers get faster and more efficient, more models will become viable to play in real time, and more crazy instruments can be created. Possibilities are endless. Thank you.